Okay, so I'm going to be discussing continuity from Chapter 2, Section 5. Now, if you want to jump ahead, feel free to click the links to skip to any section. I'm going to be discussing continuity and discontinuity on graphs very briefly, then the types of discontinuities, the definition of continuity, and lastly, the intermediate value theorem. So how do we know a function is continuous from a graph? Well, if we see that the graph is a single unbroken curve, meaning no holes, no breaks or jumps, and no vertical asymptotes, then we know that the function is continuous. So if we look at the types of discontinuities, let's say we have a graph and this is C and this is L, just any real number. And we have a curve that is continuous at everywhere except x equals c. Let's say we have a hole. If we look at the limit as x approaches c of the function f of x, and this is f of x right here, the limit is L. This is called a hole discontinuity. Okay, so now we have another graph, and let's say there's a vertical asymptote. This is an infinite discontinuity. So if we look at the function f of x as x approaches c, from both sides, the limit is infinity. So we have another graph over here. Let's say down here is negative L, and there are two holes in the graph. This is a jump discontinuity. So if we look at the limit of f of x as x approaches c from the right-hand side, the limit is positive L. If we look at the limit of f of x as x approaches c from the left-hand side, the limit is negative L. So therefore, the limit of f of x as x approaches c does not exist. We also have non-removable and removable discontinuities. So if you look at the function f of x equals 5 over x minus 2, looking at it from the onset, we know that if we plug in x equals 2, we have a constant over 0. This indicates a vertical asymptote. So here the discontinuity is a vertical asymptote, and it is at x equals 2. On the other hand, we have a removable discontinuity. If we look at the function f of x equals x squared minus 3x over 2x minus 6, that can easily be factored out into x times x minus 3 over 2 times x minus 3. We can cancel the factor x minus 3 out, and because of this, this is a removable discontinuity where the function is discontinuous at a single point, x equals 3. And if we quickly head over to graph this, we'd see that the function is continuous at everywhere except x equals 3, where the y value is undefined. So to know if a function is continuous without a graph, we look at the definition of continuity to tell us whether the function is continuous at a point or not. And so the first condition that needs to be satisfied is f of c is defined, c being any real number. There's an error on the last two. It should read the limit as x approaches c of f of x exists, and lastly the limit as x approaches c of f of x equals f of c. Okay, so now we're going to test out these conditions on this problem right here. At what points is the function f of x not continuous? Here we have a piecewise function, f of x equals x minus 6 if x is less than or equal to negative 1, f of x equals x squared minus 3 if x is greater than negative 1 and less than 2, f of x equals 2x minus 3 if x is greater than or equal to 2. We're going to look at x equals negative 1 first, because it's on the interval of the first two equations in the piecewise function. So if we look at the limit as x approaches negative 1 from the left-hand side, we're going to use the top equation because it's closer to negative 1 from the left-hand side, and we get negative 7. If we look at the limit as x approaches negative 1 from the right-hand side, we're going to use the center equation because it's closer to negative 1 from the right-hand side, and we get negative 2, not 4. Therefore, the limit as x approaches negative 1 does not exist. If we refer back to the definition of continuity, we see that this does not satisfy the second condition. And so this actually answers our question, at what points is the function f of x not continuous? And one of the answers is x equals negative 1. So now we're going to look at x equals 2, and we're going to look at the limit as x approaches 2 from the left-hand side, and we're going to use the middle equation because it is closer to 2 from the left-hand side. And so we're going to get 1. If we look at the limit as x approaches 2 from the right-hand side, we're going to use the bottom equation because it is closer to 2 from the right-hand side. And we also get 1. Therefore, the limit as x approaches 2 is 1. So that satisfies the second condition of the definition of continuity. Now we're going to test for the first condition, f of c is defined, and our c is 2. So we're going to look at f of x equals 2x minus 3, and if we plug 2 in, that will equal 1. So this satisfies the first condition of the definition of continuity. Now if we look at the last condition, we see that the limit as x approaches 2 of f of x equals 1, which is equal to f of 2 equals 1. Now all three conditions are met, and so we know that at x equals 2, f of x is continuous, but this does not answer our question, which is asking for where f of x is not continuous. So this will not be part of our answer. So when you're working on these types of problems, be sure to check that the x intervals are continuous at the x values you're evaluating. For example, in this same problem, if f of x is equal to x minus 6 only when x equals negative 1, then we can't evaluate the limit at x equals negative 1. Okay, so the next problem is asking for what values of b is the function continuous everywhere. We're given a piecewise function again, where f of x equals negative 2 plus bx if x is less than or equal to negative 2, and f of x equals x squared plus 2x minus 6 if x is greater than negative 2. So from the previous problem, we know that if we plug in the x value that's on the endpoints of the intervals into the two equations to find the limit, and the limit is the same y value, then that satisfies the second condition. So in this case, we want to set the functions equal to each other, plug in x equals 2, and solve for b. We get b equals 2. So to ensure that the function is continuous when b equals 2, we're going to very quickly see if all the conditions are met. So the top equation of the piecewise function is now f of x equals negative 2 plus 2x. And looking at the first condition, if we plug in x equals negative 2 into the top equation, we get negative 6, which satisfies the condition. If we check the limit from both sides, the limit as x approaches negative 2 of f of x equals negative 6. And knowing all of this, all three conditions are met. And we can conclude that our answer is b equals 2. If we graph this piecewise function and zoom in a bit, we see that at x equals negative 2, y equals negative 6, and that this graph is continuous. And lastly, the intermediate value theorem. So the intermediate value theorem states that if f is continuous on the closed interval of a comma b, and k is any number between f of a and f of b, then there is at least one number c in the closed interval a comma b, such that f of c equals k. So we just need to look for a few things, which are continuity and the y values at a and b, and that's going to tell us if the number c exists and equals k. So to illustrate this, we have a closed interval from a to b, and let's say up here is f of a and down here is f of b, and this part is in between a and b is all continuous. And if this is true, if it is continuous, then there exists this number c right in between the interval, where f of c is going to be k. So we're going to apply the intermediate value theorem to this problem right here, which asks to use the IVT to show that f of x has at least one zero in the closed interval a comma b. And so f of x equals x cubed minus 5x plus 2, and the closed interval is 0, 1. So now we're going to check for continuity, and because f of x is a polynomial, we know that polynomials are continuous everywhere, and so yes, it is continuous on the closed interval of 0 to 1. So now we need to find f of a and f of b, and those are the y values of the endpoints on the closed interval. And because our closed interval for this problem is 0, 1, we're going to find f of 0 and f of 1, and we're going to get 2 and negative 2 respectively. If we look at our problem, it's asking to show that f of x has a number 0 in the interval, meaning that our k is equal to 0, which happens to be in our interval f of 0 equals 2 and f of 1 equals negative 2. So now that we've confirmed this, we can write our statement. Since f of 0 equals 2 is less than k equals 0, which is less than f of 1 equals negative 2 by the IVT, there exists at least one c in the closed interval of 0, 1, where f of x is continuous, such that f of c equals 0, or f of c equals k. When you're working on these types of problems, don't forget that f is continuous on the closed interval. And click the screen if you need some practice problems.